So in the previous lecture, we took up the new unit operation drying, and in that case, we said that each solid has certain characteristics of drying. In other words, if you want to design a large scale dryer, we have to start with the solid which we want to dry, say the sand or zeolites or alumina. And the more important here to note was that for in drying, this characteristics curve, so-called the characteristics curve for drying, not only depends upon the type of the solid, all right, it also depends upon the rate of the drying. That means the operating conditions under which you are doing the drying, that also makes a very significant difference, because we said that the drying is one unit operations which is accompanied by both heat transport and mass transport. So we have to look at the different the conditions for heating. Say, are we doing by microwave heating, or have we exposed the entire surface area to some heater? Is there the flow through the solids, or is there any air flowing just over the surface? All right, all of this will determine, say, equilibrium concentrations of moisture. So this is slightly different from the previous, say, adsorption isotherms, when we said that we fix the temperature, then the isotherms, given the partial pressure in the gas phase or concentration in the liquid phase, equilibrium concentration is fixed here. But here you must have noticed that there are so many other factors, they also play a major role. So essentially what we are saying here, that we have to take a sample of certain solid and determine its drying characteristics. So we will do a very simple experiment, suspend it in air, monitor its weight gain or weight loss, so drying or wetting. Okay, there also we said that there is a hysteresis, so the rate of drying is different from the rate of wet here. And more important here is that we should ensure that the operating conditions, Reynolds number, or the area of exposed for this batch of the solid at lab scale and and some pilot plant or the industrial scale is as close as possible. Okay, so first thing here is establishing the characteristics of drying, and we are talking about the batch drying to begin with. So we have suspended a solid, zeolites, activated carbon fibers, charcoals. We have given certain Reynolds number. Okay, so the solid dries and we monitor its weight loss, and we get a characteristics curve. This curve is very important. We must understand it makes a the basic of your all calculations as far as the batch drying is concerned. Before that, if you recall, we also had one more characteristics curve. There we plotted partial pressure, so equilibrium vapor pressure of moisture versus moisture content, and of course we not dimensionalized the equilibrium vapor pressure by the vapor pressure of pure water. Okay, so that's one type of curve, very important curve, one in case of drying, and the second is drying rate curve for this batch solids or batch drying. Okay, so let's begin with this. We are trying to address here the rate of batch drying, all right, or we're trying to establish here drying rate curve. Okay, and we said that we have to ensure that our lab scale or lab conditions are properly scaled, or they are similar to the real operating conditions under which we want to do this batch drying. So we are doing here this batch drying. So what we will do here, so we have a solid and we monitor this weight loss. So there is certain flow rate, okay, air, temperature, relative humidity, initial weight, certain diameter, certain type of solid, everything is right fixed here. So if we monitor its weight loss, we should expect this type of curve. So we have theta, let's say time in hour, and here we plot x, how much is the weight loss or kg of moisture remaining in the solid. So kg of moisture per kg of, say, dry solid. Here also we said that there are two ways of doing this. One is on the wet basis and the other is on the dry solid. Okay, so we have both heat transfer and we have mass transfer, right, both. So at certain degree heat is transported to the solid and mass is getting out of this solid here, which is moisture. Now if you do this experiment, you will expect that to begin with, if the solid is cold and this temperature of air is say very large hot air here, that there will be some initial adjustment time. So which means there will be some rate here, say from A to B, which would be slightly ill-defined in the sense that air could be colder, or the solid could be colder than this air, or it could be hot. Alright, so here there is some initial adjustment, very small amount of moisture will be lost here. So initial adjustment period, you can say. Then typically what happens is a very typical curve of most of the solids. Of course there are always exceptions there. So then after a certain time, a very small amount of time, when the solid temperature has reached the air temperature, okay, steady state, then there is a weight loss, and this weight loss will go linearly like this for some time. Say let's mark it here C. The change in the moisture content is linear. Alright, so after the solid is warmed up or cold, has reached the temperature, one monitors very typically this linear change in the weight loss. Then there is a slowdown. Okay, so let's see, we have till D here. So now we can say that there is a non-linear. We will see this later, that this linear curve will represent constant rate of drying, and this non-linear, or from C onward, we will call it falling rate. We'll come back to this later. So at some rate this decreases non-linearly, and then typically again things get slowed down, so we have another decrease, very small decrease, till the moisture content has reached say certain equilibrium values, Xc or X star. Okay, so this is what we call it a characteristics, a typical characteristics drying curve here. Alright, of course a different solid will behave differently, but it's most common that to begin with one observes a linear, then non-linear, and then again it's non-linear, and further rate has slowed down here. So now if we define, like in the previous class, rate of drying as N, so the most common and practical way of defining this rate of drying would be, so let's say the amount of the solid, dry solid, so without any moisture, let's say SS. If its area which is exposed to the drying is A, so we can define as dx dt. So in other words kg per second per meter square. So that's the rate of drying defined like this. So you can see that SS is the initial weight which is fixed, A is the area which is exposed. So either you have a solid like this, slab like this, and you want to dry from here, or you have a solid like this and you're drying, you have some air flow past this. Area is, of course, external area, exposed area is fixed here. Now here also we said that after some time, when the solid is covered with some thin film, there will be patches that will develop here. So of course the wet area will be different, but what we are writing here is the initial total area. So this area is actually fixed as far as the definition for rate of drying is concerned. It's not the wet area, not it's a dry area, it's a total area. So dx by dt, knowing x here, we can do this del x over del t. We can take a small time step after we have monitored all this rate, and we can calculate this rate here. So this is the curve 2, second type. Remember, if you had recall, first we plotted relative humidity here, relative saturations, right? P bar over P0 versus X, or versus X here. Okay, so that's the number 1 in drying curve. Now we have the second drying curve, which we have drawn X versus theta, and from this we calculate N, and then again we plot N versus X. So this would be the third curve, which is quite important in our context. We'll revisit them quite frequently. So once we have X versus theta time, now we calculate N here, which is rate of drying. So now at what rate moisture, kg of moisture, is depleting from the solid surface, hour, let's say we have meter square. So that's the unit of this rate here. Now we are starting with a very high amount of x. Let's say that to the extent that solid surface is covered with a very thin film of liquid, kg of dry solid. So that's the unit of this x. So let's say that we are starting for a very large amount of this moisture. So schematically you can say that we have the solid surface and there is a thin film of liquid or moist solid. You can also say completely moist solid to the extent there is a thin film of liquid. Right. So you can also have a solid which you have suspended and there is a thin film of this solid here, or thin film of liquid, excuse me. Alright. So if you recall the first, going back to the previous one, you have linear or there is some initial adjustment. So when the solid gets heated or warmed up, so you can have maybe like this or you can have like this, starting with A. So we can call, initial adjustment, and this is purely because of heat transfer. Solid either is getting heated up or is getting cooled up. So either the rate decreases drastically, takes some adjustment over a very short time, and or it increases, or the rate increases. Okay. Then since the x changes linearly, dx by dt, which we are plotting here, dx by dt, we have ss over a. So since x is decreasing linearly, we will expect that dx by dt will be constant. So a, then we start with b. So now the rate is constant till we hit the region which we called earlier as falling rate curve. So let's mark this region as C. Why? Because xc we will call it as critical moisture content. Critical moisture content. So this represents that kg of moisture per kg of solid till, or if the moisture content is greater than xc, rate is constant here. Why rate is constant? We go back to the previous curve or previous discussions we had thin film of liquids, right? So it's just like a constant rate of evaporations. Whether you're drying from a solid surface or you have a pool of liquid, alright, it's all the same here. Critical moisture content. Now after that, so we can call it, this is a constant rate. Okay. Or you can also call as saturated region. So these are the different terminology. All of this, they reflect the same meaning, that solid is covered with thin film of liquid. Now after that, we said that x decreases non-linearly. So the typically what happens here, the rate decreases linearly. Alright, so we are plotting dx by dt. Now the rate will decrease linear. So as you said, there's a typical drying curve, and different solids will exhibit different type of behavior, but this most common here. Rate is a constant, then rate decreases. So till here we can say that this is a falling rate. So we have constant rate and now we have a falling rate. And here we said it's a saturated region. Now we are saying that this region, so let's mark here till it falls linearly, we'll call it, so C, so we have xc, and d, let's give some number here, let's say xt. So this is a region which is a part of this falling rate, except now we are calling it unsaturated region. Unsaturated region. So this is the region. Now you start seeing the dry patches. So some surface has been dried up and some surface still there is a thin film of liquid. Now you recall also that it's possible, or in fact it is like this, that if you measure this kg per meter square of wet area per second, then whether you are in this region or in this region, the rate should be the same, which is same as the rate of typical evaporations. Since we are defining to be consistent area, which is the total area, there is a decrease in this. So as far as the mechanism is concerned, whether the saturated region or unsaturated region. Most fundamental, the two mechanisms are the same. What we are seeing here, the decrease, is the artifact of this area which we have chosen. It's total area. Mind you, the actual area, since because of there are patches, actual weight areas are smaller, getting smaller. So if you measure per weight area, the two will be the same. So we have saturated region, unsaturated region, constant rate, falling rate, and go back to this now, because there was earlier when we measured x versus time, there was one more region where the drying rate has gone very, very slow. So you will expect some other rate, it will fall like this. When now it has reached x star or xe. So this we define. Now the solid has reached an equilibrium concentrations. Alright, so this is also equilibrium concentrations. You should go back and recall from our first figure when we drew P bar over P0 versus T, vapor pressure of pure water, and the partial pressure or equilibrium vapor pressure in this. There, if you recall, we had drawn like this, typical curve like this, till it reach at some point x star equilibrium concentrations, moisture contents, which is in equilibrium with the drying conditions or quality of air, which we said, let's say P some air over P0 pure water. Okay, so this x star corresponds to this x star. It's the same here. Now this solid cannot be dried below this. It has reached a concentrations which corresponds to the partial pressure which moisture exerts at the surface, and that equals your whatever the quality of air, relative humidity, RH, or relative saturation you have in the air. So now you cannot go below this. If you want to go below this x star, you will have to lower, you have to dry, you use a drier air than what else you are using. Now come back to this this drying curve here. Let's go back, constant rate, falling rate. So right here till here it's both are falling rate. So C to x star, if you call it E for equilibrium, so that we can mark this curve B, C, D, E. So BC, it's a constant rate. CE, it's a falling rate. And CE has two components. CD, it's a linear decrease. So rate decreases linear. And this we call it unsaturated region. And then now we have DE, that's more important. Here also we should discuss that what is the mechanism here. Here the mechanism is the same. Whatever mechanism we had here is the same mechanism, except now since there are wet patches, so the area is different. Since we are plotting with the A, total moisture content divided by the total area will be decreasing, will be smaller here. Now here also is a falling rate, so second component, except this is a region where now internal movement of moisture, or you can say that now this is a region where now pore diffusion, capillary effects, see, or these are, they reflect the same meaning here, capillary effects, all of them, they start taking place here. That's why we have different characteristics from here to here and from here to here. So what we are trying to say here, that if you have the solid surface, bring in contact with some quality of air, dry air, as long as it's filled with, covered with some thin film of liquid, it's just like a common evaporations. Either you are evaporating from a solid surface or from a lake or from some river, pool of water, the two will be the same rate of evaporation you will expect here and you will expect here. This water will not see the solid here. Alright, so we have plenty of pool of liquid here. So the two rates are same as long as the temperature is same and the drying air, quality of the drying air is same. However, when now you have patches, dry patches appears, and then there are thin films here. Here also this rate of evaporation is same as this. The two are the one and the same. All three in fact are the same. But why we see a decrease here, falling rate? Because we are expressing our rate based on the total area. Had we expressed based on the wet area, then of course this would have been would have been the same here. So since the total area and this rate decreases because we have evaporations, moisture evaporates only from here. All right. Then comes the third region where still it's a falling rate. However, now the capillary forces become important. So now we are saying that the solid surfaces, deep solid surfaces, they are capillaries, and the moisture has to be supplied. So this moisture has to diffuse. Moisture has to diffuse by pore diffusion, by Knudsen diffusion. All this we have talked when we took up the previous unit operations, adsorption, desorption. Same mechanism holds good here. This moisture has to come to the top of the surface, then it will evaporate. All right. So now we are talking of the hidden moistures. These are the surface moisture. These are the moisture which comes from inside, from within inside. So we have seen the third type of falling region where the rate was non-linear. Here the rate was linear. Here the rate was constant. Okay. And of course before this we talked of initial adjustment, where the solid gets warmed up or comes to equilibrium with this air temperature. So one, if you call it, second is a constant rate, third is a falling rate except linear, and the fourth is non-linear falling rate. Until at the end we have reached X star equilibrium concentrations. You cannot dry your solid below this. Moisture content will be at the most X star here. And the more important here, this X star is one quantity which depends upon temperature, of course. It depends upon the type of solid, that's one thing. All right. It also depends upon the air quality. So look at this equilibrium. This is, you cannot say that truly this is your thermodynamic equilibrium, which we have seen in case of adsorption, desorption. Here the drying has to do a lot depending upon in the heating arrangement, rate of heating. All of this to decide the heat of rate of heating, rate of drying. All right. So the more important here is of course the third curve which we obtain, which is the characteristics of the solid. But more important here is that we must be very careful that what we do in the batch, in the lab, must also replicate or as close as possible the operating condition or the drying condition on on larger scale. All right. So what we do now, we will like to re-emphasize here that there are three characteristics curves. Traditionally, when you say that characteristics curve, one represents this rate versus x, n versus x. That's very important. But we must also understand that we also have one more curve when we talked of bound moisture and unbound moisture, free moistures. All right, here also you have x minus x star, which is free moisture. So x minus x star or xc is your free moisture. All right. So going back to the previous discussions, now we have three curves. One, partial pressure over vapor pressure of pure water versus x. That was 1 kg moisture per kg of solid. There we talked of bound moisture, unbound, free moistures. Remember the curve we have. Second one is x versus time. That's a true experimental data for that type of solid and that type of operating conditions. Cross flow, through flow. Surprisingly, this x star remains that quantity which has not been quantified exactly for the type of the solids. For the reasons here that things are so complicated, pore diffusions, Knudsen diffusion, or the heating arrangement, heating effects, heat of radiations. Are you heating by microwave heating or are you heating by conductions? To have the flow through, cross through, or you just have a flow over the surface. Equilibrium concentration is a strong function of the operating conditions. Okay, unlike any other previous thermodynamic equilibrium we had, we talked of absorptions. Given partial pressure, how much is the solubility? Henry's law. So if you fix the solute, ammonia and water, temperature, equilibrium curve is fixed. Then we talk about the relative volatility distillations. We have y versus x curve for benzene, water, toluene, xylene. All right. If you fix the pressure, then we have y versus x is fixed. Txy is fixed. There is no operating conditions there. Then we talked of extractions, solubilities, immiscible fluids. We fix the temperature, we fix the system. We have this triangular equilibrium diagram. A, B, C, they are distributed by some phase diagram. Then we talked about adsorptions. You fix the temperature, then moisture content, moisture loading, or any solid loading given the partial pressure in the gas phase or given the concentration in the liquid phase, we have isotherm, Langmuir, Freundlich, whatever we have. Here, x star, because of this x star, which is strongly dependent upon the operating condition. One has to ensure that you have established this equilibrium curve, which is x, which is rate versus x, before you design a real system. And for that you have to ensure that the two conditions, the batch and the lab conditions, or the pilot plant or the industrial scale, they are as close as possible. Okay. So now what we do, we will set up some equations. We like to study how long will it take, given this n versus x curve for certain solid, certain system, how long will it take to dry this solid from one moisture content to another moisture content. So we will set up the governing equations, then we will like to take an example and we will put some numerical numbers there and we will compute some quantities. Alright. So let's take this. The second topic is time of drying. Okay. So again, we have to start from here. We have n versus x. If we leave aside, this is starting initial adjustment, then you have b, then you have c, decrease linearly, then non-linearly. So c, d, e, you can mark this xc, critical moisture. Corresponding to this, we have nc, critical rate of drying. But notice that this is a flat, so critical rate of drying is constant between b and c. Then it decreases, so this is a falling region. Let's say we reach till xt, then we have reached till x star or xe. So we'll follow this nomenclature: b, c, t, e. You can have a dotted line, which remains ill-defined for most of the cases. Initial adjustment, we ignored this time here. Okay, rate is defined n as minus ss, amount of solid, dry basis, total area which has been exposed for drying, over dx over d theta. Theta is the time in hour. So what is the total time? We just integrate theta, 0 to theta, let's say d theta, equals ss over a. Since it's a minus sign here, we can say x2 over x1 dx over n. So we want to dry the solid from x1 to x2. Typically you can start from x1 here, you can go all the way till xe. But here this x1 and x2, any two quantities in between, maybe they are on the falling linear here, maybe they are here, maybe x1 is here and x2 is all the way till down here. So it's a very general expressions for calculating this total time of drying, which is integral of this quantity. So first case is that immediately once you know n, you can find it by the area under the curve. From n, you calculate this curve 1 over n, plot x, and whatever you have this, you calculate the area under the curve, and then calculate this quantity theta. But realizing that the area here, this rate remains constant and the rate decreases linearly, we can have analytical expressions as well. We can avoid this numerical integrations, whatever we have, we can have here. Okay. So the first thing is that constant rate period. So we are talking of BC, right? We neglected the initial adjustment. So we have this BC. BC, the rate is constant, and NC. So when you integrate this, very simple integrations, theta will be SS over A. N is a constant, so NC comes here, and you have x1 minus x2. So this x2 now will correspond to actually whatever concentration you have between B and C. So this x2 is greater than x1, greater than xc, but this is smaller than x1. Alright, so you understand. So x1 and x2 is any quantities between A and C. x1 is of course the starting one. So this is a very simple expression for constant rate period. There is no need for numerical integrations. You read NC from the graph, and x1 to all the way till xc, you can do these calculations. We'll come back to this. We'll take the example. Number 2 comes falling rate period. So falling rate period, now we are talking of C to E. Alright, all the way till it's falling. Of course, there are two region, A where the curve is linear, starting from critical moisture content XC to this D, which is XT. So here the rate is n equal to mx plus b. Alright, you can assume n equal to mx plus b. Then you can integrate linearly. You put it back there. Very simple integrations. Theta equal to ss over a. We have x2, we have x1, dx over mx plus b, which if you integrate, you will get ss. You have m, slope of this curve here, a, ln m x1 plus b over m x2 plus b. Alright, you must realize that this m is a slope of the curve. So any point between 2 n1 minus n2, x1 minus x2. Mind you, this x1 x2 we are talking of in here. So now we are trying to integrate between this. This is the slope of the curve. n1 is nothing but mx1 plus b, n2 is nothing but mx2 plus b. Alright, you can just put it there. If you would like to substitute this m here to obtain this expression for ss over a, x1 minus x2, n1 minus n2, ln n1 over n2. So now we are talking of x1 and x2, which is greater than xt, but it's less than xc. So we are in this region. So x1 and x2, let's say this is x1, this is x2, this is the rate n2, this is the rate n1. So we got these expressions for linear falling curve. Okay, this can also be rearranged to, if you notice that you have ln term here from our some previous context here, it is ss over a, x1 minus x2, and we can call it nm. What is nm? You should recall there's nothing but log arithmetic average. Alright, so now we have these expressions for this, and now the third curve, which is also a falling rate, so we'll call it the region B. A is DC. Now we are talking of this. Now D and E till we have reached equilibrium XC. Okay, so from here to here, of course, we do not have any analytical expressions. All it means we'll have to integrate numerically. So one we like to plot 1 over n, and then this x. All right, whatever curve we have, take that curve, find the area under the curve to obtain this theta here. So the same quantity which you have here has to be solved analytically. All right, very often what happens that one makes an assumptions that after this constant rate which starts decreasing at critical moisture content, one makes this assumption that this curve is all the way till xc. Now again, this depends upon type of solid, where we can say that, well, this region is quite smaller than the total region, total theta, or it's possible that there's not much of change here whenever you have this inflection at d. In that case, one can make a linear assumptions right from here to here to say that the rate is an approximations. This is m, slope of the curve, x minus x star. Since we know this nc, which will be satisfying the equation of this line right from on this whatever we have here, we can say that this is nothing but slope is nothing but nc, x minus x star minus xc minus x star. So there's another approximations one can do for this nc here. So if you have nc is known, xc is known, x star is known, equilibrium concentrations or xc, same here, then theta can also be integrated to show that ss xc minus x star over nc, critical rate corresponding to critical moistures, into ln x1 minus x star over x2 minus x star. So it's an approximations one can make, or you can do the numerical integration as well. Alright, so we have non-analytical expressions as well as this numerical expressions to calculate total time of drying here. So starting with this n versus x, n versus critical this moisture content, if we identify all the points, constant rate decreasing, then further decreasing till it is xc, one can start with this generic very basic definition for rate for drying and see which range is constant. You can do analytically, numerically, or you can make this approximations and you can do the numerical integration as well. So with that, now we take an example for this time of drying for a batch system. So we take this example here, very simple example but very basic. This is about batch drying. Problem reads like this, something like this, that we want to decrease the moisture content from 25 to 6%. Alright, so we have to decrease the moisture content here. The more important here, it reads that what condition is this? We want to decrease under conditions identical to those for which the given drying curve applies. So this is what we have been trying to say earlier. It's very important that we understand this. Here first one has to start with the drying curve. Alright, so this is again very different to what we had, different under the unit operations like adsorptions. There the isotherm is fixed for the system, not for the operating conditions. Here the problem says that I have the solids, it has a moisture content 25%. Alright, I want to decrease from 25% to 6%. However, the conditions are the same under which I have a drying curve available. So this drying curve was generated a priori. It was generated before I want to design a real system, and we are hoping that this drying curve will represent the two conditions which are identical. Of course, it's not practical, doing the experiment in the laboratory, or in the pilot plant, or in the industrial scale. But that's the way it is. The drawing is there. It's more of a engineering drawing. There are some approximations here. So maybe we have kept the two Reynolds numbers same. Here we have the same heating conditions, heating by radiations, same level of radiation, convection, same Reynolds number, same heating by conductions. So that means we have the thickness of the solid same as what we are going to face there in the real world. Alright, so with that, so we are starting with the drying curve, and the drying curve is looks like this. So we have x, we have n, the unit of n is kg, meter square per second, and this n is reported as n into 10 to the power 3 here. Let's put some number, 0.3, we have 0.2, alright, let's put it 0.1 here, and we have 0 here. So you have this BC starting with B, we are ignoring A, the rate is a constant till it hits C at this level of 0.3. It decreases linearly and decreases all the way till D. Let's say this D is 0.15. So this is a falling linear rate from C to D. Then it starts decreasing non-linearly till it goes all the way till concentration here, which is x star, and let's put this number at 0.05. From the graph, let's put this number as 0.1. Let's put this number as 0.2, and the first number here we have this on the graph as 0.3. Okay, or maybe let's put it as 0.35. So this is a 0.35 to 0.2. This is a constant. This is your constant rate here. Then it's a decreasing rate linearly, decreasing rate non-linearly. All these numbers are known to us. Now we say that moisture content is 25 to 6% moisture. Solid weight is, total solid weight is 160 kg. Okay. To surface area, or the area for drying available is 1 meter square per 40 kg of dry weight. So from this you should be able to make a guess or make a compute that what we require is SS over A. Total weight, that was the expressions for n, so the number outside the integral was SS over A. This is nothing but 40. Alright, so kg of total weight, dry weight, no moisture there, per area, so that's equal to 40. So this is given to us. Total weight is 160 kg, moisture content is 25, so the initial moisture content on dry basis, all this is all dry basis, right? This is nothing but 0.25 over 1 minus 0.25. This we have done dry basis, weight basis earlier in previous lectures. It's always advantageous most of the time to work on this dry basis. So 0.333 kg of moisture per kg of dry solid. What is X2? 6% moisture, so 0.06 over 1 minus 0.06, which is 0.064, same unit as before. So where are we right now? 0.33, so we are in this range, very close to this. That would be our starting X1, and we have to go till 0.064. This is 0.1, so we are going till here. So we want to dry this till 0.064, which is our X2. So from X1 to X2, that means we're going to cover all three range: constant falling rate, linear falling rate, and this non-linear falling rate till this locations here, which is 0.064. Okay, so it's a very straightforward problem here. Xc is one quantity we should note immediately, because we are going to use this. So this Xc is 0.2, and corresponding to this Xc is we have Nc, which is 0.3 10 to the power minus 3. So graph was reported like this, so it's 10 to the power minus 3 kg per meter square per second. So these are the two quantities of important parameters of a drying curve. Is a critical moisture content that reflects the range beyond which or below which you will have the falling rate, beyond which you have constant rate, pool of liquid, etc. We have talked those, and critical this constant rate is 0.3 10 to the power minus 3, which remains constant between B and C. So with these two, all we have to do, we can go back and substitute in our equations which we have developed. You can start from the first principle. It should not take much time to obtain the final expressions, which is X1 minus X2 over Nc. So SS over A is 40. X1 minus X2, so we are starting with 0.333. Constant rate goes till 0.2. So this is the first constant rate we are trying to calculate. Theta between B and C. Alright, so 0.33 minus 0.22 divided by Nc. We have rate 0.3 10 to the power minus 3. You have 16,000 seconds. So it takes 16,000 seconds for the moisture to dry from 0.33 initial concentrations, initial content, to theta c or xc, where now you start seeing decrease in the falling rate, in the rate. So now you hit falling rate period. Already we have said Nc is 0.3 10 to the power minus 3, corresponding to which Xc is 0.2 units you have for both. And now you have to dry till 0.065, so you have to go till Nd. Alright, so now we are going, starting from C, we go till D, till you have the linear falling rate period. Okay, so this Nd, if you read again from the graph, this is 0.15. Go back to the previous, here this Nd is 0.15. 10 to the power minus 3. We have this xt, you can read 0.1 units. So theta f1, 1 to denote the first region, falling rate period, is same as ss a xd xc. So we are decreasing from xc to xd. First we decrease from x1 to xc. Now we are decreasing moisture content from xc to xd we have dx over mx plus b, all of those we integrated. We can go back and integrate here. We can just write down the final expressions. When you substitute the slope of the curve, we have xc minus xd, nc minus nd, ln nc over nd. All these quantities are known to us. All you have to do is to substitute. SS by A is 40, xc minus xd 0.2 minus 0.1, 0.1, nc minus nd is 0.15, 10 to the power minus 3, ln 0.3 divided by 0.15. Put all of these numbers to obtain approximately say 18,480 seconds. Alright, so now we are done with this C to D where the rate is falling linearly. It's linear. Here the rate was constant. Now we come to the third rate. Let us plot n versus x for last stage of drying. So we have this rate curve, drying curve like this, n versus x for the last stage of the drying when the rate decreases non-linearly. So already we did the calculation till D when the moisture content xd was 0.1. Okay, so this is the non-linear part of the drying curve, the last stage. And corresponding to this D, we have the rate prescribed as or calculated as 0.15, and we have been asked to calculate how long will it take moisture content decreases from 0.1 to x2, which is 0.066. Equilibrium concentration, that means the rate becomes 0, xe is 0.05. So the question asked is xt to x2, how long will it take? What is the time here? Okay, we have the general expressions for drying theta equal to SS over A amount of solids over the area of drying, xd integrated to x2, we have dx over n. So this is the general expressions for drying here, and we are discussing here this non-linear part of this curve, right, from here to here. Okay, this extended till xc becomes 0.05, at which the rate is 0. So to integrate this, you can see since it's a non-linear part here, we require numerical integrations. So some numerical integration technique, you take as many as point possible here. So let's say we have x moisture content 0.1, 0.08, decreases to 0.064. So we have to go till it's below xd, which was given as 0.066. We are starting from 0.1, which is your xt equal to this. For this, the rate in 10 to the power minus 3 is given as 0.15. These are the data 0.07, 0.04. You are supposed to take as many as data point in between for a very smooth curve here. Alright, so take as many as points here. Since we have 1 by n dx, we require 1 by n rate here. Alright, which if you do it, you will get 6.67, 1 over 0.5, you will get 14.3, and then we have this 25 and some intermediate data points. All you are supposed to do is to plot 1 over n. You have x here, all right, and your trend is like this. You have xt, you have x2. Essentially, this integration dx by n between xt to x2 is nothing but the area under this curve. So calculate this area under the curve, take this as an exercise, put the values of SA, SS to calculate theta, the time taken to reduce the moisture content from 0.1 to 0.066 is approximately 24,000 seconds. Okay. So we have all three times total time for drying. First we had, remember, for constant rate, which was 16,000 seconds. So this is the rate, this is the time over which the rate remains constant. moisture dries at a constant rate. Then we have falling rate, but we have the linear falling rate, which was 18,480 seconds. And the third, which we just now we calculated for non-linear rate. So this is linear, this is non-linear rate from 24 around 24,000 seconds. All right, so total time is around 58,480 seconds to dry this solid under batch conditions. So it's a very simple example, and here we have made use of certain analytical expressions, or we have made use of certain numerical calculations to calculate the last quantity. We also said, if you recall, that one very good approximations which can also work, that if we assume that from B to C, which is a constant rate, when you hit this critical moisture content, then the rate decreases linearly. So we ignore this D point here, or we are at least we are approximating that the rate which decreases non-linearly is very close to this. Very approximately we can say that it's linear throughout. So we hit still XC, so that means till X2, XC to X2 we can assume it's a linear right here. Throughout it's a linear. So this is approximations we also discussed, and we can use the expression directly for theta. All you have to do is now you have the same mx plus b, n, nc satisfies this here, we have xc satisfying here. We know this xc at which the rate is 0, that's equilibrium rate is 0 here. So we know this quantity, we know this quantity, we know this quantity here, xc. One can also make use of this to find the slope. What is the slope here? We can go back, calculate this n, put in the integral equations. We showed that this number, assuming that entire rate of period is linear, falling rate is linear, we have ss, xc, x star, nc, which is also known to us, ln xc minus x star over x2 minus x star. So this is another expressions, approximate approximations, assuming that entire falling rate is linear, so that we avoid this numerical integrations. Of course, depends upon type of the curve here. Maybe in this case one has to plot and convince himself that the error is not much here. So SS by A is known to us, this is 40, XC is 0.2, X star 0.05, equilibrium moisture contents, X2 you have to dry till 0.065. SS by A, the whole quantity was 40. Put all these numbers to obtain that you are getting this very close to 18,480 plus 24,000, two numbers, which is 42,480 seconds. Alright, so in today's lecture we have taken this example, and before that we had developed analytical expressions to calculate different time of drying for constant rate and falling rate, linear, non-linearly, for a batch system. And before that we said that there are three very important drying characteristics curves. One is partial pressure versus x, then you have x versus time, and from that you calculate rate versus x. All three of them have important meanings in terms of understanding the mechanism of drying. What is the bound moisture, what is the unbound moisture, what is the falling rate, when does it happen, why it's a linear artifact of the area, why it's linear. The mechanism of evaporation is the same in two cases. Then there is a non-linear curve where we said that the drying is controlled by capillary forces or capillary effects. There is a Knudsen diffusivity. Then we talked about this equilibrium concentrations, equilibrium content, which depends upon not only the type of the solids but also on the operating condition. So we marked all those regions, all three curves which should be familiar, that play a major role in designing a real system, real dryer. Okay, so that's about the batch drying. We have the example. Next time when we meet, we talked of now flow through. So we have the solid, batch of solids, through which now the drying hot air passes through. Here we have the solid, and over which the air flows over. So it's more like a semi-batch kind of thing. Okay. And the second one is also semi-batch. Solid is stationary, but now air will pass through this. And before we taking that, we will also talk about heat transport, how we are heating the dryer. Remember we said that drying we have to give a due considerations to heat transport. The solid has to be heated by conductions, by convection, by radiations. So we'll make use of our understanding, very basic understanding of heat transfer coefficients, convective heat transfer coefficients, radiation, etc., to address those issues here. Okay.